Greetings everyone and welcome to this tutorial on how to perform a t-test in R. Before running a t-test, we'll be loading a few important libraries which will help us achieve our goals faster. The gtsummary library is useful to get a summary statistics table. The report library or package is an amazing package to get automated statistical reports. The law stat package will help us to run our Levene's test for homogeneity of variances. And the ggpubr package will help us to visualize our data and plot our data in nice graphs. For the purposes of this tutorial, we'll be using the empty cars data set from the datasets package. And we'll be storing that in an object df. So we would like to view our data and how it looks like. So we'll be running the view function. And here we can see that these seem to be models of cars and these seem to be some parameters of our cars. So what exactly are these parameters? We can do that by running a query over our data set. And here we have all the names for the abbreviations. So MPG stands for miles per gallon, CYL stands for number of cylinders, so on and so forth. Specifically for this tutorial for t-test, we'll be running a t-test to check whether there exists a statistically significant difference in the average in miles per gallon given by a car over whether the car is an automatic transmission car or a manual transmission car. Now we will attach our data, which helps us to easily run codes over variables. Now we will get a few summary statistics using the tbl underscore summary function from the gtsummary package. And we will group this over the variable am, which is, as you can see here, the type of transmission. 0 stands for automatic, 1 stands for manual. So we'll be running the tbl underscore summary function. Now, the gtsummary package by default gives us the median and interquartile range for continuous variables and frequency and percentage for categorical variables. If you want to change that, you can run a query over tbl underscore summary and you can see how to do that. In a later video, I'll be explaining exactly how to do that. Now, prima facie, we can see that the cars with manual transmission. So one code is a code for manual transmission. You can verify that here. You can see that the median average in miles per gallon given by a manual transmission car is higher than the median of an automatic transmission car. And we can also check other variables here. So this is a good starting point for us before running our t-test, because we now know that the median or the measure of central tendencies is higher in manual cars. Now, before running a t-test, we need to check some assumptions. The first assumption is independence. So observations in one sample are independent of the observations in the other sample. So in this example, this is fairly obvious because observations in automatic cars are bound to be independent from observations in manual cars. In this data set, we are expecting that these cars are randomly taken, are randomly sampled, the models of cars. The third assumption is that of normality. So both samples, so the automatic and manual samples, are normally distributed. And we can check that using a few techniques. So we can check that using visual techniques. Those include plotting histograms. Note that MPG is our variable of interest, and if we code AM with two equal to signs and our level, it will only pick up the values with automatic transmission cars. And similarly here for manual transmission. So in a square bracket, if you put two equal to signs in beside each other and you write your value, then it automatically picks up only these values. We can also perform a visualization technique using QQ plots, and these points should approximately fall on a straight diagonal line. In this graph they are. And we can also perform a statistical test, the Shapiro-Wilk normality test. A significant p-value for this test denotes deviation from normality, and we can see that both of these p-values are not significant. That is, uh, both of these values are approximately normally distributed. To check the last assumption, that is homogeneity of variances, we can run the Levene test using the Levene.test function from the lawstat package. And we can see that the p-value is just borderline significant. We can discount this p-value, we can discount the significance. And again, similar to the Shapiro-Wilk test, a significant p-value suggests that there is heterogeneity of variances, that the variances are not homogeneous in both the groups. In this case, it is just borderline significant. We can assume that the variances are approximately similar in both of these groups. So we do not need to perform a Levene's t-test. So now to perform the t-test, the function in R is t.test. You don't need to load a separate library to perform this test. It is included in the base package. And this is how you write a code to run the t-test. So your dependent variable is on the left-hand side of the tilde, and your grouping variable or independent variable is on the right-hand side of the tilde. This is an unpaired t-test. This is an independent samples t-test. So we are writing paired is equal to false. So you can write false in all in caps, or you can just abbreviate that and write F for false. Also, we can see that the variances are approximately equal, so we won't be correcting for inequality of variances. But if we did want to correct, we could write T to correct for heterogeneous variances. And we'll be storing the results of this test in an object TT. So we will run this function, and using the report library, we can obtain a statistical report for our t-test. This is especially very handy for novices because you automatically get a nice report. Now, in this report, we get our difference of means, you get our confidence interval of the difference, you get a p-value, you get your effect size, Cohen's d, and 95% confidence intervals for effect size. And we also get a nice report. So you can copy this as it is in your manuscript. And we also get how these effect sizes are labeled as large, small, or medium effect sizes using Cohen's recommendations. So here we can see that the p-value is indeed significant, and as we saw in our summary table, manual cars do give us a better average or a better mileage than automatic cars. And on average, we get around 4 miles per gallon higher in manual cars than automatic cars. We can plot a simple mean and confidence interval graph using the ggline package from the ggpubr library. And these are various parameters we can include. So on the x-axis, we'll be plotting our groups. On the y-axis, we'll be plotting our continuous variable. This is a line of code to denote what exactly we want to plot. So here we'll be plotting mean and CI. You can also plot mean and standard error, mean and SE. You can plot mean and standard deviation. And we want to have a nice colorful graph. That's why we'll be writing a line of code for color. And here you can see your mean with confidence intervals. And you can see that the manual transmission cars have a higher mileage. You can also plot box plots using the ggboxplot package, and approximately the uh, the arguments are the same as the ggline function, and you get a nice box plot. So that's it for this video. Thanks for watching.